can't, type in the chat. Well, you probably won't type in the chat if you can't hear me saying this. So if you can, type in the chat. Yay, okay, sounds good. Okay, let's get going. Okay, so you had this background reading from last week. Hopefully you read it. We're going to be talking about that paper today. And let me turn down this light. Okay, and let's see. Okay, so for next 2 weeks, which I think is November, maybe it's November 15th. So I'll fix that. Let's see. So I think 2 weeks from today is November 15th. So let me fix that. And okay, so the second half of the survey paper that you hopefully have read the first half of. So this one covers basically block RAM, DSP blocks, various other things, recent things in FPGAs. So you're doing the second half of the paper. Again, this is, if you're going to do 2 readings in this course, I would say the part 1 and part 2 of this survey paper are the ones that will give the best overview of the course. So I highly recommend that you make that one of your readings. And then it's going to take us another couple weeks to get there, but we're going to get into routing architecture soon. So this paper is on routing architecture, ways to basically leverage the metal stack, and the fact that we get different things out of different metal layers. How does that interact with how we might make a routing architecture? No lecture next week, so unless I got this wrong, next week is reading week. Is that right? Okay, so no lecture next week. I think we're not supposed to do lectures in grad courses during reading week. Everybody agree with that? Are all your other profs also canceling lectures next week? Okay, then I'm just making sure I'm not standing up from the herd, right? Like, I don't think people are. So it actually it's a bit awkward, because it would actually be convenient in terms of the course timing to do a lecture next week. Because I'm going to release the 3rd assignment, which is on a RAM mapper. I'll put the slides up that we're going to would cover next week, but instead it'll be a week after, which include, what is RAM mapping, how do we architect RAM blocks on FPGAs, because this assignment is about doing that, okay? I won't make this due till the end of November, approximately, or late November anyway. I recommend you read this assignment in advance of that, though. So we're not going to have a lecture for 2 weeks. I'll post the slides. You can get started on this well before that. This is different than the first 2 assignments. This is no longer like writing HDL. You're now writing software. So you're writing a particular kind of CAD tool called a RAM mapper and using it to answer some FPGA architecture questions. And large parts of this, you can write well before we have that lecture. And That. I'll post the slides to help you. I'll also release the information about the survey paper or research survey paper that you have to write by the end of the year, so that you can, it's not going to be due for a long time. It won't be due till late December, but I know you're all going to be at home, bored out of your minds during reading week. You're like, what am I going to do? No lecture, assignment's not due for a long time. Survey paper, you can start doing background research for it. So. Okay, so today we're moving on to logic block architecture. So last couple lectures we talked about styles of FPGAs, then we went through a detailed analysis of a simple FPGA. Now we're going to start going through some research results on various important components of FPGAs. Okay, so one of those is logic block architecture. So we've talked about some of this already, but just to review, we usually break logic block architecture into 2 pieces. There's the logic element, or the basic logic element. People use both terms. Most commonly, this nowadays is a lookup table with some number of inputs that the architect has chosen, plus a flip-flop. Okay, so this would be a very common, simple, basic logic element. And as we talked about, it's kind of inconvenient to make that be your whole logic block and then surround it with island-style routing. So most FPGAs, pretty much all actually, group a bunch of those logic elements into something bigger that they call a logic block or a logic cluster. What that is take n of those basic logic elements along with some local routing A common local routing has been a full crossbar, which is okay as long as you don't make this logic block too big, but it's definitely not the only one. Okay, so people also use essentially switch networks that have fewer switches than full crossbars, but more limitations. That's also common in there as well. And you have some number of inputs that come into that, and normally all of the outputs go out. Okay, so what I've shown you, I'd have well, the basic logic element I've shown you has one output, could be the registered or combinational output. The logic cluster allows all those to go out to the general island style routing. It also allows me to feed back signals that are generated in the logic cluster to the inputs of the logic elements in it. And it allows me to take some number of input signals from the general routing, okay, through some routing muxes, and bring them in, and this local routing gets them to where they need to go, okay? The number of, okay, so the total number of, if I ignore the clock is usually brought in on a special network. So if I ignore the clock, in my simple logic element, I've just got simple flip-flops. So the only control signal I have is a clock. I don't have any clock enabled, etc. in this simple one. And I have it coming in on a special resource. And then I have all my data signals that'll go into my basic logic elements. Okay, so how many of those data signals are there, right where I drew that circle? Using the variables that I told you. This is like a check. Is anybody following me? This involves multiplication, okay? So it's close to reading week, but I believe you can still do multiplication. What's that? 4n, yes. And in general, that's because k is 4. If I change the lookup table size, it would be kn, right? So right, 4n, or the general case is kn. Usually, most architectures bring in fewer inputs than that. So it turns out that logic, you can have, your CAD tools are pretty good, or can be made pretty good at finding logic elements that feed other logic elements and putting them together in one logic cluster, or finding logic elements that have some signals in common, right? They both take in they're two gates, and they happen to have a common input. So I don't normally need to have kn inputs coming in from the outside of this logic cluster. I could build that, but every input I bring in means more routing muxes out here. And we saw that those are actually pretty expensive when we did that hand analysis last week. So it can be beneficial to bring fewer in as long as the CAD tools can handle it. And the CAD tools can handle it if they can find things that, you know, basically reuse signals enough that they can still fill this up. Okay, so that's the basic structure of a logic block, with variations being what is k, what is n, what is I, and then another variation that we'll talk about a little more briefly, which is just what is this local routing? Okay, could be a complete crossbar, but could be something else. Okay, so we already talked about this. Most FPGAs use a basic logic element that is LUT-based. So this is like review. Why? Why are LUT-based highly used? Yeah, what do you think? Right, so they can represent any function. So that means they get a lot of functionality for few routing ports. And we saw that routing ports, you know, a connection into the programmable routing tends to be expensive, right? Commonly, they're like 20 to 1 muxes or so. So they're pretty expensive. It also is nice for our CAD tools because it's easy to tell if some grouping of logic will fit in a LUT or not. Just count its inputs. Yeah? Yeah, so I don't know, how many people know what rotation means? There's probably a term that comes from the industry that you may not know. So, okay, so we know the geometric rotation, so that's good. But what LUT rotation means, well, maybe I'll get you, Isidore, why don't you explain what does LUT rotation mean? Sorry, Jerry caught you eating a carrot. Let's say my truth table was this, okay? I'm just doing a 2-LUT. So let's say my truth table is 1, 0, 1, 0, right? Actually, that's kind of a boring truth table, sorry. I felt truth table regret as soon as I wrote that. Let's say 1, 0, 1, 1, okay? So what Israel's saying is the router, the CAD step that tries to connect everything together might find it's hard for me to get a certain signal that was coming from, somewhere over here on the chip. I follow all these routing wires, and it turns out that this signal, which is my A signal, I can't actually connect it into this input, but I could connect it into this one, okay? And wherever A was coming from over here, well, B was coming from over here, and it turns out B can connect there. Okay, that's the wrong signal. It doesn't work, except for the fact that we can just say, okay, that's all right. The router hooked these up backwards, right? Hooked up B to where I wanted A to go and A to where I wanted B to go, but it can now change the truth table. And let's see if I can actually change this truth table properly. I might want to go back to a simpler truth table. So if I flipped which one is A and B, Isidore, how do I flip this truth table? Yeah, so in this one, these two are where A is 0. Okay, you know what I'm going to do? I'm going to write down, this is AB here. Okay, so AB is 0, 0, 0, 1, 1, 0, 1, 1. Okay, that's my truth table. So if I flip which one is B and which one is A, right? Like I hook these up backwards, then let's see. Yeah, these two are going to flip. So I can rewrite this truth table as this. Hopefully that's legible. And it actually compensates for the fact that I hooked up the inputs in the opposite order. And you can always do this. So FPGA CAD tools leverage this. They basically say, if I'm routing to a lookup table, it's actually an easier problem. I don't have to get to a specific input, get me to any input, and then we'll just have a little CAD algorithm that fixes up the truth table afterwards. Yeah, did I do it right?
Yeah.
Excellent.
About that as well, aside from making the routing plugging in here, is that the pins on the LUT are not all the same delay. The Fmax through the pins, there's faster pins and slower pins.
Yeah.
So you can rearrange, if your Fmax happens, whichever path happens to be your Fmax, if it goes through a slow pin, you can try ripping up and rerouting it to go through a faster pin.
Yeah, that's a good point too. So I'm taking like 2 weeks off. Isidore is going to do this. That was actually a very good answer. So it's another good point, which we'll look at in the in the routing architecture. I mentioned this a bit, but basically, as you saw, a lookup table is built as a tree of multiplexers. So the different inputs have different delays. Whichever one's sort of at the end of the multiplexer tree is faster than whichever one is at the beginning of the multiplexer tree. And it's kind of fundamental. Can't really get rid of that. So if you tell the router you can go to any input you want, and your router is good at estimating timing, so it's what's called a timing-driven router, it can speed up your circuit by taking essentially the most critical signal, like the latest arriving signal, and sending it to the fastest input. And then we'll just fix up the truth table afterwards. And yeah, that whole thing is called LUT rotation. So maybe next year I'll actually draw that on the slides nicely, because that's a good point, and my drawing is kind of messy here. Okay, but we like LUTs. Most FPGAs use them. It's really interesting. Okay, so here's another aside. SRAM is not scaling that well. So this is actually an interesting challenge for lookup tables. Lookup tables they kind of use a lot of SRAM. And as we go to the latest process technologies, SRAM is actually one of the hardest things to scale its size down. So maybe that means that lookup tables will change to something else in some future process node. I don't think they will. I think they'll find a way to scale it some, but it is interesting. Lookup tables have been dominant for a long time, but the fact that SRAM cells don't scale very well, essentially it's hard to shrink their transistors aggressively and still be able to write it reliably, read it without upsetting the signal, and basically have a nice stable cell. So that is challenging, 10 nanometer FPGAs. They made it all work. But I know at 7 nanometers and 5 nanometers, the FPGA vendors are going, this is a real pain that SRAM doesn't scale that well, and we use so much SRAM in things like our lookup tables. Okay, but what is the best lookup table size? So let's say we're going to use the dominant architecture, we're going to use lookup tables, we have to choose this K. How big should it be? So there are a whole bunch of architecture questions here. So do we combine the lookup tables into a logic cluster, this 2-level hierarchy that we talked about before? We talked about some of the reasons that would be good. It can let us have these word-wide signals. So I only showed clock on my simple logic cluster, but usually we also have clock enable and clears and so on. We need to decide, if we decide we like this logic cluster idea, we need to decide how many logic elements we put in. We need to decide what is K, how big should our lookup table be, how many of these inputs do we want, and also how much interconnect in the cluster. So should it be a full crossbar or something else? So actually, just in the logic block, there are a whole bunch of architecture questions. Okay, so how do we answer that? I'm done with chalkboard, right? I've gone as far as I can with chalkboard and rinse rule analysis. It helps inform you, but you have to actually answer these things empirically. So you take benchmark circuits that represent the applications that you think are interesting. You have some kind of compiler. So compiler is a CAD tool that's going to map your benchmark circuits to that architecture. You're going to estimate area, delay, and increasingly power. And you're going to decide, is this an efficient architecture or not? If it's not that good, you change something, try again. And you may repeat that a lot. Okay, so here's a possible CAD flow. Okay, so I take benchmark circuits. I'm going to, I have to get them into gates. So maybe these benchmark circuits are gates. Maybe they're Verilog. I have what's called an elaborator. It's the first phase of synthesis that turns them into gates. Then I'm going to optimize the gates. So there are tools, synthesis tools that can try to reduce the complexity of your gates without breaking functionality. Then I'm going to technology map them, which means I don't actually have gates on my chip. I have LUTs, and it's a certain size LUTs. And now I've got an actual synthesized net list. And I can say, okay, my area is, just count how many LUTs I used on average. Well, that's N LUT, sorry. How many LUTs did I use? And I'm going to use my techniques of counting transistors and estimating layout area to get an area per LUT. And I'll say my delay is depth. Depth is how many LUTs are there in series. If I look through my whole circuit, between two registers, the most LUTs I ever had in series was 5. Okay, then my depth is 5. And I take that times the delay of a LUT. And I can get that by, I just designed my LUT using the transistor level circuitry that we talked about before. I could spice that and get its delay. So, okay, so this is my proposed flow. And a nice thing about this flow is I got to get some CAD tools, but I only need synthesis CAD tools, right? So I don't have place and route in here. So I don't have the complete FPGA CAD flow. I just have the first part. Turn my circuits into gates, then turn my gates into LUTs. So what do you think? Do you like it?
I love it. The problem is that if I had a routing architecture with no routing wires, I would get the same answer as a routing architecture with a million routing wires.
Yeah, so this is, it's totally neglected routing. Okay, now I'm not trying to answer questions about routing. I'm trying to just answer questions about the logic block. But it seems like you're concerned that I just have no routing here anywhere.
Exactly.
Yeah, so this is pretty bad. I mean, it does simplify my CAD flow to not have placement and routing, but I don't even have anything estimating routing at all in my area model or my delay model. And we just saw, we didn't do delay, but we saw for area last week that it's actually bigger than the logic area. So the thing I've neglected is actually, it's not like a minor thing, it's like the first order effect. So I can't do this. I need to improve it. Okay, so let's say I also need to graduate. Okay, so I don't want to go off and route a place and route tool. Can I make this better quickly? Okay. Is there anything I can do that's easy that would make this at least somewhat better? Yeah.
Have some crude estimates of, let's say, routing and saying there's no suggestion, for example, just say
Yeah.
XY distance is not the
Yeah. So even if I don't want to go off and write the rest of the CAD flow, which is a lot of work, I at least can make a simple model and make it explicit. It's better than no model, and at least clarifies what am I assuming. So, so yeah, this is bad. Don't do that. And it's not that hard to get a crude model. So here's my crude model. I don't change the CAD flow at all because this is actually a lot of work if I have to write that. I'm going to say my area is the area of the lookup table circuitry, the number of inputs to the lookup table times the area of, the interface to the routing, that input port, plus the area of the output interface to the routing, and take that whole thing and multiply it by the LUT count. It's crude because I've just made these things into constants, and I might have to get those constants with some, maybe whiteboard stuff like I did last week. but it's still a lot better, right? I actually have a model of routing. It understands that I get more input ports if I actually increase the size of the LUT, so it's capturing some of these effects. And my delay, I could say, well, this probably doesn't change much, but my first order delay model would be, well, take the delay of the LUT plus some estimate of the delay of the routing, which is normally bigger than the LUT delay, and say, take that times how many LUTs I have in series. Now, this particular one is not going to change any conclusions, really, because it's still just the delay of the LUT plus like I'm always adding the two delays before I multiply by depth. Now, if I change my estimate of the delay of the routing as I change the LUT size, it might have more impact. So anyway, so this is a lot better, and it wasn't much work. So just don't ever neglect routing area. At least put in a first order model. But it is hard to estimate, right? So if I want to go off and estimate these things, the delay of the routing and the area of it is going to be tricky. I need a lot of experience to get a reasonable estimate there, and it's still probably not that great. So what do people usually do? They use a more complicated architecture evaluation flow. The one I just showed you stops at synthesis, which makes it easier to run, and if you had to write it, it's less work to write. It is a lot of work to write a full CAD flow, so usually people don't write one from scratch. They use one that exists and maybe add in some features. The most common one is something called VPR and VTR. VTR is the whole flow, and what's shown in blue is essentially the VPR part of it. So you'll see both terms. That's kind of what they mean. And you'll use this in the fourth assignment in this course. And good news, when you're running a tool, it's easier than writing it. So the fourth assignment by design is actually a bit easier than the other ones because you don't have to write this CAD tool. You just have to run it. So what do you do? So you still have to gather benchmark circuits or go grab a standard suite. You describe your architecture now. So one of the things that's kind of most unique about this CAD flow is that one of its input isn't just a benchmark circuit, which Quartus or Vivado would also have. It also takes an input of what is the chip. And that description is pretty detailed. So it describes the architecture of the chip, so what are its logic blocks, what's its routing. Also information about how the circuit design happened and the process. That's a fair amount of detail, but it's still human readable. If the architecture is not that complicated, it's still not that long. CAD tools can't work with that kind of description. This is like a human readable textual description. So there's this phase inside VPR that's called an architecture generator that takes that description and turns it into really big data structures, like big graphs and big maps of the chip that are suitable for a CAD tool to work with. It gives all the detail that would have been created essentially by hand inside something like Quartus or Vivado for specific chips. So this is automatically created for what you asked for. That, basically makes these big data structures. These data structures can be for a big FPGA, gigabytes, tens of gigabytes. So you wouldn't want to specify these by hand. It's like every wire, every switch, every block on the whole chip. And that's why this architecture generator is helpful. Right? You can take a human readable description and it can kind of fill all the blanks in. This architecture drives a bunch of this CAD flow. So the CAD flow for FPGAs basically starts with something called elaboration. So this is the CAD flow from like Verilog or VHDL. If you had high level synthesis, it basically is one more step that would be above these. Okay, so if I had HLS, you would basically have that one extra step above these. So first stage of an FPGA CAD flow at the HDL level is elaboration, which is basically pattern matching. It parses all the Verilog or VHDL and figures out what does it mean. That's a mux, that's a flip-flop, that's a multiplier, that's a RAM. And it does a little bit, in the VTR flow, it also does a little bit of optimization. Then it passes that on to a tool called ABC that comes out of Berkeley, which optimizes the logic. So it turns an AND gate followed by an inverter into a NAND gate, that kind of stuff. And then technology maps to primitives, so things that actually exist on the chip. So flip-flops, LUTs, little multipliers, little pieces of RAM. VPR then basically packs those primitives, those little things, into bigger logic blocks and bigger function blocks. So we're going to talk about logic blocks this lecture, And after reading week, we'll talk about DSP and RAM blocks. Those are other function blocks. Then it basically chooses where to put all of those larger blocks, logic, RAM, DSP, and then it chooses how to wire them together, turning on some programmable switches, leaving others off in order to connect, make all the, millions or tens of millions of connections that might be needed by a big design. And it can only use the wires that exist and the switches that exist. So that's why it has to be talking to this architecture representation. And once it's done all that, it basically estimates what's the power of the design, what's the delay of the design, how much area would this chip, this architecture that you've specified take, and now you can basically assess how good it is. And all of these blue phases here, well, actually not all these blue phases, all the ones that have this dotted line are connected to timing analysis. So timing analysis is basically going through the design and all the estimated delays for all of the connections to work out how fast is it, so what would be my frequency, and what are my speed limiting paths. And that's done in the VPR flow, I don't know, about 150 or 200 times, because as these optimizers run, they're updating their guesses of what the delay of various connections are. Early on, their guesses are pretty crude. Later on, when we're in routing, their guesses are pretty good. And every time they periodically, after they've made a bunch of decisions, call the timing analyzer with all these guessed delays to say, okay, what's my speed limiting paths now? And I'll put extra attention on those, try to get those blocks closer together, try to connect them very directly without any detouring in the wires, et cetera, to make it as fast as possible. Being timing driven is pretty important for these phases of an FPGA CAD flow, because otherwise you can get a very slow circuit. Does it make sense? Yeah.
Could you give a time, you know, like some information, like what is the delay from this point to this circuit and so on? Is that gotten from price, or how do designers try and customers try and get this?
Yeah, that's a good question. Okay, so basically part of the architecture description is it's like delays. Okay, so like the delay inside a lookup table would be part of that architecture description. The delay of your local interconnect would be part of it. The delay of every wire, every switch is part of it. Does that make sense?
Yep.
Now there are patterns to that. You don't usually make like, you didn't make like, I laid out 550,000 unique switch layouts. You made like a limited number of different kinds of switches. So that's why that architecture description is more succinct. You say, I made 4 kinds of switches. Here's the delay, resistance, capacitance of each one of them. And I use them to hook up wires in the following ways. And then this architecture generator would turn that into essentially a flat representation of, okay, here are your 100 million wires, here are your 200 million switches, along with their delays and resistance and capacitance data. That's enough that basically the timing analyzer can get estimates of delays. Now, early on, before you do packing, you don't even know what's been grouped together. You don't know where it is. You don't know which wires are going to be used to connect it. So it's definitely a crude estimate. As you go through placement, the estimates get better because you do know what's been grouped into various logic blocks, and you actually know where you've put things, at least for now. You still don't know how they're hooked together, but you can estimate, I think it'll use this wiring. When you get into routing, it's quite accurate because you're like, right now, I am using these exact wires to hook you together in these exact switches. So as you go through this phase, the timing analysis is getting better and better delay estimates by basically calling into these algorithms saying, give me your best guess. But this happens in all CAD tools. Early on, you can change things a lot, right? You can make big decisions of put these lookup tables together or don't. Move this block halfway across the chip or not. But your estimates of delay are more crude because you're earlier in the flow. Later on, your estimates of delay are very good, but you've made most of your decisions. So you try to do a reasonable job of predicting here, and you try to fine-tune later. That's the basic way people try to do this. But when you have freedom to make really big decisions, you also have relatively poor estimates of where the delays are. There are ways people handle that. Sometimes they put iteration loops on this and so on. They say, well, we'll go all the way back to the beginning, and we now have more information. But this flow already is actually quite slow because these are every one of these is a computationally difficult problem. which means putting iteration around it is like slow squared. So usually you try to avoid that, even though it means you're making some predictions that will be wrong and you'll lose a bit of quality. So,
Get more servers.
yeah, you could buy more servers, or you could. I mean, when I was at Altera, every like in the latter years I was there, it happened every single year pretty much. Someone in the field application engineering organization would say, like, can you make the place and route tools in particular, because they tend to be the most time consuming, faster by accelerating them using FPGAs? And I didn't know how to make that work, so I just went to academia. So it is hard to make this a lot faster. So okay, so that's the basic flow. So I'm going to show you like a classic paper that looks at a bunch of these trade-offs using that exact flow. So yeah.
One thought about the flow and the bias to introduce is that this flow is not using the production system from Cordis, which is optimized for the particular device.
Yeah.
There may be particular architecture changes that will appear to be good changes simply because this is not micro-optimized to the architecture. The software tools are not micro-optimized to your architecture, so you can get low fidelity sometimes with this flow.
Yeah, I mean, it's a good point. So the architecture evaluation flow will affect your answers, right? So your ideal would be you optimized everything to the nth degree for every architecture, but it's not really achievable. So the VTR CAD flow basically tries to adapt to the architecture, which means it's never as fully tuned as it could be to any one architecture. If you make certain radical changes, it might be quite detuned, and therefore you could reject them. What some industrial vendors do, so Altera or Intel uses a mix. So they actually use an internal version of VPR. And I believe in recent years, as they've gotten into like more esoteric, well, added a bunch more complexity to their architectures, they use Cordis to do more of the fine tuning. So Cordis is a production CAD tool. So the advantage is like I'm changing things in the production CAD tool. I know this is going to be pretty close to the customer experience. So that's good. The disadvantage is a lot harder. It takes a long time to do, so it restricts the range of what you can look at. That's kind of fundamental, right? Like you use very highly tuned tools for this class of architectures, you probably will not deviate far from them. On the other hand, if you use a more generic tool, maybe it's not going to optimize as well for any one architecture, so it might also get results that are noticeably different. One of the advantages, though, either of those approaches is still much, much better than trying to guess, because either of them have some validity. And what you get is this flow, for example, if it says I got this quality from this architecture, you could actually ship that architecture and you know that that quality exists. You may be able to get better quality by tuning the tools more, but you at least know this amount of quality exists. And a very common unintentional exit strategy from the FPGA industry has been to just make the hardware and then assume that the CAD tools can be created and can get the results that your more crude models predicted, and that may not be true. The CAD tools might not be possible to be written or not written by your team in the time they have. So it's much less risky to say, look, I have a hardware software system and together it gets this answer. Even though maybe I could get a better answer with more tuning, at least I know I got at least this. It's a way safer thing than the alternative. But yeah, good question. And you can't fully separate it out. Okay, so I'm going to go through a classic paper by Ahmed and Rose. This is Jonathan Rose from, it's Elias Ahmed and Jonathan Rose, who's here at U of T. And it looked at basically several of these different parameters. So the first thing they're looking at is, should we have these logic clusters at all? Okay, so right now they're looking at a single basic logic element. So just a LUT and a flip-flop, and it's a simple logic element where you can take out the registered version or the combinational version, but not both. And they took a suite of benchmarks and ran them through an earlier version of that VPR CAD flow. And they got a couple things. They got this curve is the area per cluster, okay? So this solid line. And they're plotting it versus LUT size. Okay, now the cluster is just one basic logic element, so it's kind of a degenerate cluster. But the area of that logic cluster goes up pretty rapidly with LUT size. So at a size 7 lookup table, it's there. Size 2, it's way over here. And we kind of expect this, right? We know that the area of the LUT itself is exponential in the number of inputs, so it starts getting very expensive. And then this dotted line is how many LUTs do they need. So on average, they needed 1,600 of these lookup tables when they were just 2 input, but they, actually this is not a count, sorry, it's an area in terms of, let's see, no, I'm using the wrong axis. Okay, so this is a count, but I should be looking over here. So if they used a 2-input LUT, they need on average about 4,500 of them. So these are relatively small circuits. Nowadays you'd use much bigger ones. And if they use a 7-input LUT, they only need about maybe 1,300. So the count of how many lookup tables they need goes down a lot, but the area per lookup table goes up a lot. So in order, and this is also including the routing that goes along with it. Okay, so they haven't neglected the routing area. If they put this together to say, okay, well, let's count on multiply how many logic blocks we needed times the area, including the routing, what's the best? And they find basically a broad minimum, that a LUT between 4 inputs and 6 inputs, they're all pretty good, much better than either smaller or larger, and maybe LUT 5 is a little bit better than the others, but it's a pretty broad minimum. Okay, so if you basically were just going to make an island-style FPGA, you're not going to use these logic clusters at all, choose a 4-input to 6-input LUT. But then they looked at, well, maybe these logic clusters are a good idea. So they're now going to take this basic logic element, k-input LUT, and they're going to do exactly what I talked about before. They're going to put n of them in a logic cluster. They're going to build local routing, and their local routing is a full crossbar built out of multiplexers. And that local routing will be smaller if they have fewer inputs. So they're also going to see how many inputs they need to put into this. All of the outputs can also be taken back out to the general routing, and all of my outputs from these BLEs feed back into my local routing, so they can be reused. Let's see. In order to answer these questions, they have to assume a routing architecture. So the architecture space is really big, so they can't simultaneously explore everything. So previous work has shown that length 4 routing wires, so you go past 4 logic blocks, that's a pretty good choice before you end. So I used all length 4 routing wires. I think I just said this, they use a full crossbar here. There are multiple ways you can make the routing switches. They basically make half of them out of pass transistors and half of them out of tri-state buffers. So we'll look later on at what the trade-offs are, but they choose a reasonable routing architecture. And then all of this is using layout estimates and delay estimates, so it's actually tied to the process technology too. So this was done in an older process technology, 180 nanometers. So you can't separate their conclusions out completely from the routing architecture, but they made reasonable assumptions for it. So I'm going to show you delay results, and just to make sure you understand what this architecture looks like. I've got island-style routing out here. I go through that input connection blocks, what I called the I port, or input port to the logic block last week. So that's a multiplexer controlled by SRAM cells. There are some buffers, because I'm now going to drive a bunch of local routing. That local routing is also built out of multiplexers. So because I have n signals that were generated in the cluster and I that are coming in from outside, each multiplexer has n plus I inputs. And I'm going to have k times n of them. And then I'm going to actually have my lookup tables, my flip-flops, and then I'm going to go back out of the logic cluster to the general routing. Okay? And the way they connect to the general routing is slightly different than what I showed you last week. They're doing it with big pass transistors rather than using kind of the multiplexer structure that I used. So anyway, but they carefully model all these different delays in the area of all these different things. So their first result is they want to work out, well, how many inputs do I need for each of these clusters? And the average number that a cluster uses, basically on the x-axis, is how many of these LUTs go into a basic logic or into a logic block. And as they make the logic block bigger, that's no surprise, they need more inputs. And the average number goes up according to this dashed line. But they decide to build the average number of inputs. They say, I want to be able to use almost all the logic in these logic blocks. So this is the number of inputs they found that they needed to basically use 98% of the LUTs in their logic blocks. So they wanted to be able to fill them full. And to do that, they needed somewhat more inputs. They still found that they didn't need to make, like the number of inputs to the basic logic elements is k times n, right? So k input LUT, and there are n of them. Kn is how many inputs they need if they just wanted to make sure they always had enough inputs. They only needed about half of that, okay? K over 2 times n plus 1. Does this make sense? So they didn't need that many inputs, and how does this line up with Rent's rule? So I'll throw that out and see if anyone has any thoughts on that.
Because you have local use of like the local cluster is not going to need the same number of inputs in and out of the cluster as in the cluster.
Yeah, so it does kind of make sense. This is another that's showing that locality again exists. Which of these two curves does Rent's rule predict? Does it predict the dotted line or the solid line? Yeah, so Rent's rule is always about the average number of terminals. So Rent's rule fits the dotted line, which does look sublinear, which makes sense, right? Because Rent's rule was, remember, the number of terminals is equal to, well, some constant times the amount of logic, which in this case would be n, to some Rent exponent p. And p was always between 0 and 1. So if my CAD tools are good and my circuits are not kind of really not poor locality, I expect this p to be less than 1, so I expect this to be sublinear. And it is sublinear, so that's good. This number of inputs I need to use almost all my LUTs is actually not quite linear, but it's almost linear. So it's a bit worse. And if the authors of this were willing to space things out a bit more, they could probably push down the number of inputs. But maybe that wouldn't be a good choice, right? They decided we want to be able to use almost all our logic, so we don't want to architect for the average or the average plus, a little bit. We're going to architect for kind of the worst case that our CAD tools need, which is a bit bigger. Okay, so a whole bunch of graphs here, which I'll go through kind of quickly to get to the conclusions. This is a picture of, like, what am I looking at? I'm looking now at just the area inside one of these clusters. So remember, clusters, n of these BLEs and a bunch of local routing. And this is the size 1 cluster, this solid line. And then as I go to bigger and bigger clusters, so basically this is increasing n. So this has 2 things in the cluster, 3 things, 4 things, 5 things, etc., up to 10 things. Okay, so the area goes up per cluster as I put more things in it. That makes sense. And as I make my lookup table bigger, which is when I go along this dimension, things also get bigger. And if I go to really big lookup tables, they get a lot bigger. Okay? And there's kind of a noticeable jump when I go from a cluster of size 1 to 2, because that's when I have to start putting some local routing in. Okay, so that tells me how much area is there. And this isn't the area of one cluster. It's like, count up how many of these clusters I need for this circuit, and then how big is that? And this says if that was the only thing I cared about, I would use a pretty small LET, and I wouldn't use logic clusters. I'd be way down here. But it's not the only thing I care about. I also have to hook all these logic clusters together, so that's how much area do I have in between, in the island-style routing. And it shows the exact opposite trend. As I go to really big lookup tables, I don't need that many clusters anymore. So my area to hook up all of those clusters is smaller. Okay, I just don't need as many routing channels. Even though the routing channels might be pretty wide, I don't need that many logic blocks. The total routing area is not that high. And then here, as you look at how does this vary with cluster size, well, this is cluster size 1. And then as I go down to cluster size 2 and 3 and 4 and so on, basically the area of this routing in between the logic blocks keeps going down. So this is showing the exact opposite trend of the previous plot. Yeah?
I'm just curious, why did one of them pop way bottom? You know, larger cluster size end up being a lower area than a, or higher area than a smaller cluster size?
So which one are you asking about? Like,
The way, if you look at number 4, the way bottom,
yeah,
and
this
you
one?
follow that line across.
Oh, you mean here?
Yeah, pretty much.
I don't have an answer for that. I guess the thing I'd say is cluster size 4 and 5 are not radically different architectures.
Oh, I see.
Like they're right beside each other in architecture space. The CAD tools are imperfect. So I probably just wouldn't pay that much attention to the fine detail there. Yeah, that's what I mean by the CAD tools are heuristics. They don't get a perfect answer. So I'm going to interpret that as like a tie when they're that close. Okay, so you have to add these two curves, right? Like what's happening inside the logic cluster, what's happening in between to get the overall area. And this is too busy if we do them all, so we're just looking at the smaller clusters here. And it basically says, here's a cluster of size 1, okay? So no local routing. And if I take the no local routing case, it basically gives the same curve I had before. It said like use a logic, a LUT with like 4 to 6 inputs. This is a logic cluster of size 2. It doesn't do any better. You've added local routing. There's some cost to that, but we're not capturing that many connections yet inside the logic cluster. As we make the logic cluster bigger, things get better. Okay, so this is like these are clusters of size 4 and 5, and they're looking better than the other ones. And if we look at the other clusters, the bigger ones, we basically find that cluster size about 6 to 8 gives them the best answer for area, and LUT size of 4 to 5, which is basically what I've circled here. All of those are pretty good. So there's a broad minimum. So reasonably large clusters, moderate sized LUTs, that gets you the best total area. When you look at performance, basically bigger lookup tables are better for performance. Why do you think that is? Why are bigger lookup tables better for performance? Makes sense? Yeah, Alex, what do you think?
You put bigger functions with much, much faster logic.
Yeah, by bigger functions, you just wind up, if you use like a 2-input lookup table, you might find that the longest chain of LUTs in your design might have 20 levels in it. And so it's 20 LUTs. Those LUTs are relatively fast because they're small, but they all have routing hops in between them. And so I go through 20 LUTs and also 20 routing hops. If I go to a 7-input lookup table, it can capture a lot more functionality. Maybe instead of 20 hops, it's like 3. And now the LUT is significantly slower, but I only have to go through 3 of them, and I only have to go through 3 routing hops. So it is logical. For the same reason, this gets faster as we go to larger logic clusters as well. So this is a cluster of size 1. As I go to a cluster of size 2, it gets faster, all the way up to, they start kind of lining up on top of each other. But the big ones like, 8, 10 lookup tables in a cluster look good. The local routing is basically faster than a general island style routing. You're just going through one multiplexer if you go from an output back to an input in the same cluster. If you made this cluster super huge, those muxes would eventually get slow, and the wires would get long and they get slow. But at this size, they're still not too bad. So making the clusters bigger, we're taking more connections out of the island style routing, putting them in this local routing. It's making our device faster. FPGAs are often architected for the best area delay product. And the reason is something we talked about before. Like basically, you can increase performance with more parallelism, which is if you have a smaller area, you can fit more copies, or with a higher clock frequency. If you have a smaller delay, you can run faster. If you multiply area delay together, it's the inverse of throughput if you have a lot of parallelism. So this is the area delay product. It's probably the most important trade-off curve. And it basically says that lookup tables between about 4 and 6 all have pretty good area delay product. This is a logic block with size 1, like no local interconnect. It's worse. It's noticeably worse than these logic blocks that have local interconnect. So it's kind of empirical proof that making this larger logic block is actually good. And it gets faster as we go to larger. It gets better as we go to larger lookup, larger clusters. But there's a pretty broad minimum, right? So any logic cluster between about 4 and 10 LUTs is like pretty close. There's fine degrees of difference here, But broadly, they're all kind of reasonable. And you will actually find FPGAs that use kind of all of these parameters. So this broad minimum has been kind of accepted and adopted by various vendors. Okay, so we haven't talked about this. So bigger LUTs capture more logic. You get fewer levels in the critical path, but they're slower. They get linearly slower as you make K bigger because they get more levels in the mux tree. But their area goes up rapidly. Their area goes up exponentially in K. So you're fine until about K equals 6, but beyond that, you just start hitting an area wall. The cluster size, you make it bigger. You take more connections out of the island-style routing, which is good. You get more connections on this fast local routing. But they're using a full crossbar, so the area is growing quadratically with n, the number of things that we put in into this logic block. And the local routing delay will get, the wires are getting longer roughly linearly, so the local routing delay will also slow down about linearly with n. Which means we can make n 10, that's no problem. That worked out well, but we couldn't say, I love these trends, let's just make n 100, right? That would be a bad choice. So.
Although then again, like it'll be sub n squared, probably
Yeah, I could make it, and I have to step away from a full crossbar. It will be dominated by n squared if I make it a full crossbar. If I make a more sparse interconnect network, then I can push it a bit further. Let's see, so this kind of just summarizes their results. So the best delay was for make the logic block really big. Use K equals 7, so 7 input lookup tables, really big clusters. Best area was a 4 input lookup table. This one's pretty big, okay? So its area is bad, but its delay is good. Best area delay had a broad minimum. LUT size of 4 to 6, cluster size 4 to 10. Within that, though, they're different. The 6 LUT is actually quite a bit faster than the 4 LUT. It's 14% faster than the 4 LUT, which is actually a lot in your baseline architecture. You'd love to have that speed. But it's also significantly bigger. It took 17% more area. So it wound up being about the same on area delay, but for different reasons. More area, but also lower delay. Yeah? That is a great point. So that's exactly where I was going to go next. So this was an important paper. How many people read this paper actually? So, okay, so some catch up on reading week. So no worries. So this is an important paper because this basic idea has been adopted now by most FPGAs. Okay, so Almond and Rose explored, what do we do in our logic block size, our LUT size? We can tune that up. And until about 2004, 4 LUTs were dominant. But people knew from studies like the Almond and Rose study that 6 LUTs were faster, but they also knew that they took more area. So the trade-off wasn't compelling. So the Stratix 2 paper was an effort to, can we get the speed of a 6 LUT? And the reason 6 LUTs are faster is, again, we don't need as many levels of logic. Right? Instead of maybe having 5 levels of logic, maybe we'll get by with 4, and that will make our chip faster. But we want to make the area cost smaller. So this comes from that Stratix 2 paper. And what they did is they took the results from Altera's synthesis flow. Okay, so this comes from Quartus. And they looked across a bunch of benchmark circuits. How many inputs do we use to each lookup table? And when we don't use all the inputs, it's kind of like you're wasting some of the functionality of that LUT. So they did this 3 times. So they basically told the synthesis tools, you have 6 input lookup tables. Okay, that's what's in the architecture, so feel free to use 6 input lookup tables. When they did that, they found that only about 35% of the lookup tables that actually came out in the net list for the typical circuit were actually used all 6 inputs. About 20% used 5, about 20% used 4, and the rest use even fewer inputs. So it's kind of wasteful, right? Like I built this 6 LUT, its area is a lot bigger than a 4 LUT, and then 20% of the time you just leave 2 of the inputs dangling, right? It's like frustrating. The CAD tool is not doing what you would hope. If they ran it again with 5 input LUTs, and now, well, 40-some% of the time it uses all 5 inputs, but still, you know, about 25% or so it's using 4 inputs, and sometimes even less. And then if you use 4-input lookup tables, now about 55% of the time it's using all 4 inputs, but still 45% of the time it's using less. So yeah, this feels wasteful. So they basically said, well, if only 35% of the LUTs that come out of our synthesis tool are actually using all 6 inputs, why are we making so many 6-input lookup tables? Or why do that? Is there a more efficient way we could do it? So let me ask you first, why do you think this happened? Does this just mean their synthesis tool sucks? Like, okay, so no hesitation from Alex, right? So just nice. Could be. What do you think?
Not all logic can actually be fed into it, or not all logic functions connecting to registers actually take in that much info.
Yeah. So it could be. You can actually never answer this, right? So it is a valid hypothesis. Maybe the tools are not very good. We need to go beat on the software engineers. We need to cut their pay. We need to do horrible things to them, right? Or maybe we need to motivate them. Maybe we need to increase their pay. I don't know. But maybe it's all their fault. And you can never you can't actually tell. But this tool had been worked on for quite a bit, so it probably isn't that, or at least there's no low-hanging fruit. But as Isidore said, there are reasons why you, let's say you just have a little bit of logic between 2 registers. It just may not have 6 inputs. It gets more complicated if you've got a lot of logic, but when you actually start mapping it, you may find this divides up into a 6-LUT and a 4-LUT. I can't do it in one 6-LUT. I need a 6-LUT between these 2 registers, and I get some leftovers. And that leftovers happens to be 4 inputs. We haven't talked about this yet, but hopefully we'll by the end of this lecture. There's another thing there's arithmetic. And FPGAs have special structures for arithmetic. That also essentially interrupts the ability of the synthesis tool to kind of just find logic that fits nicely in a LUT. If you have registers, you have arithmetic circuits, they essentially act as boundaries. And you can only really map what's in between the boundaries, and that doesn't always fill up a 6-LUT. Yeah. Yeah.
They didn't compare to, it seems to be like naive solution.
I'm guessing you're going to say that, right? Yeah. A 6 and 4, like basically make some 6s and make some 4s. And yeah, that's a reasonable alternative, which they did not look at, like a heterogeneous structure. If we're going to have some 6-input LUTs, some 4-input LUTs, let's just make some of each. I was part of the team that actually looked at this. The reason we didn't look at that is heterogeneity is hard to exploit. So this shows the overall average across a whole bunch of circuits. But some circuits actually use a lot of 6 LUTs. They work pretty well. Some not very many at all. Then you also have some parts of the circuit that can be lots of 3 LUTs between all sorts of arithmetic circuits or registers. And other parts that have a lot of 6 LUTs. So it becomes unclear, what do you do? Are you going to make like half the chip 6-LUT and half 4-LUT? That's probably not going to work very well at all. First, you're going to lay out almost 2 chips, so that's expensive. But even more problematic is your place and route system is going to hate it, right? Like you basically have a 6-LUT, and it can only go in the left half of the chip, and you have a bunch of 4-LUTs, and then go into the right half. You're going to stretch your routing wires. Yeah. So then you say, okay, that's stupid, right? So you're saying don't do like half and half. Basically put 6 and 4, maybe half inside every logic block. Okay, so you have some 6-LUTs, some 4-LUTs. That's probably better because you're not going to stretch your wiring as much. But you will still stretch it some. I actually can't remember. Maybe we did look at this. We didn't do it. I can't remember if we ever ran an experiment on it or not, but we didn't like the idea. This is still going to stretch your routing wires some because you will get regions where it's like all 4 LUTs or less, and they're going to get spread out. And if your chip is fairly full, you're just going to have to take some 6-LUT logic and stick it in there, even if it doesn't really belong there. It has nothing to do with this other one. So it's doable, and if we didn't have any better ideas, that actually might be the right thing to do. But it does have these nasty effects on essentially resource balancing. Like some circuits want mostly 6 and some want mostly 4, and some nasty effects on your place and route engine. Every time you make kind of multiple different resources, you're essentially restricting your place and route engine. So you want to get big wins for that, because your place and route engine is going to give some of the win back by stretching out wires. Does that make sense? Let's see. Whoops, let me move this out of the way. Okay, let's see if I get, I think I'm going to leave that there. So maybe I'll, let's see, I think Zoom has become self-aware. So I went, okay, so this is a total digression, but last Friday I went to the seminar here by Jeff Hinton. I don't know how many people heard about that. Jeff Hinton gave a seminar in Convocation Hall that was interesting. So it was like you had to get a ticket in advance. It was invitation only, right? So I'm part of the Vector Institute, so I could go. So I totally went. It was the scariest seminar I've ever seen. All right, it was a really good seminar. He's a great speaker, but he basically laid out an entirely plausible scenario by which like AI will become powerful enough that it essentially starts controlling us. Okay, and then some of the questions were, I remember there was a psychologist there who said, well, you know, Dr. Hinton, I think you're probably smarter than me, but I'm an interesting conversationalist, so you probably enjoy talking to me because I have a different perspective. So maybe the AI will enjoy talking to me too. Which is like, she might be right, but I'm thinking, wait, we're hanging our existence on like, we're sort of like pets? Like we're kind of interesting? Like the AI thinks we're cute? So, anyway, it may not happen. He said that Jan LeCun has a much more optimistic view that no, AI is not that smart and is not going to take over. But he had a worrisome view that it is actually getting smart enough that if you have a bad actor like Putin or Xi or Trump who makes it to manipulate public opinion, it could get actually good enough at doing that that it starts taking more resources for itself, and that would be really bad for us. So anyway, I can't remember how I got to that idea, but yeah, that's a good question. So. Well, Jeff Hinton is like, he's pretty worried. So he's pretty worried because he went through some interesting points that like we're much more energy efficient. Biological brains are vastly more energy efficient than like digital ones, but they can share information much more readily because they can actually directly weight share and we can't, right? We distill down and tell somebody what we're thinking, but they can share weights because they actually all share the same underlying digital structure, whereas we don't. Even if we could actually read out all of our synapses, you don't have the same synapses as me, so it doesn't work. But that actually allows you to distribute your training so you can send more and more data through. So he said, you know, you have these two trade-offs of the very energy efficient biological brain, but the very communication efficient digital brain. He said, his money's on the digital brain, which is interesting. And he had some examples of ChatGPT-4 and how he thinks it actually is smarter than people give it credit for, but Jan LeCun thinks it's stupider than people think. So there's no general agreement on that. His concern was basically if bad actors use AIs to do things like manipulate public opinion, which they're probably already starting to do, and then they give it a sub-goal of, well, just be really good at that. A logical sub-goal for it to come up with would be get more power for myself, get more GPUs, and this is actually a propaganda machine. And this is what its goal was. It's actually good at manipulating people. And now as a sub-goal of get more energy. And if you had a few of those, they could now compete for energy, and then now you have evolution going. So this is where he went, this is bad. This is why we should have controls on this. So it was actually quite a scary seminar. I thought the psychologist who was effectively asking, like, if I'm an interesting conversationalist, maybe the AI will keep me around for kicks. I was like, oh, this is not good. It's just like, my dog is fun and my dog is cute, but basically she does what I want. Do you know what I mean? And that is essentially like, that. I'd prefer that not be our future. Anyway, that was a long digression. It's just an interesting, I believe if you're interested, I think the seminar video is actually posted online. It is a very interesting seminar, but probably the scariest seminar you will see this year.
I think the point is we need FPGAs so we can make that happen.
It did actually make me think about, okay, wait a sec. So I've done some of my research on making machine learning more efficient. Should I be doing that? And I just came here from Micros here in Toronto this year as it's International Symposium on Microarchitecture. It's one of the main computer architecture conferences. And I was tempted to ask this question at one of the keynotes that's talking about efficient AI acceleration, but I thought there's no way this person's going to give an answer. Someone else did answer the question, asked that question of should we have any limits. They asked that of the panelists, who are all people coming from AI acceleration startups or academia, and effectively no one would answer the question. So it's like, it was interesting. Pioneer in this field is kind of like we should probably have a lot of safety discussions and so on, but economically there's no incentive to do that. I don't really have an answer to that, except I hope AI is not as smart as Jeff Hinton thinks it is. And he's not sure, so hopefully it's not that smart. Let's see. I can't actually remember how I got in that digression. That might be the biggest digression that I've done so far in this course. So, but anyway, going back to fracturable LUTs. So fracturable LUT lets a big LUT decompose into two smaller ones. So this is the alternative to what Isidore said. Isidore said build some 6 LUTs, some 4 LUTs. What if we could have one resource that could turn into either? Okay, now turning into a 6 LUT already can turn into a 4 LUT. So that's not useful. We can just use 4 of its inputs. We want to do better than that. And if we could do this, it's probably nicer than building some of each, because the place and route system is going to be happier, and we're not going to have this kind of balancing problem of maybe some circuits ran out of 6 LUTs, some ran out of 4 LUTs. It turns out if we look inside of a lookup table, you can say, well, maybe I could make 2 smaller LUTs out of a big LUT. So you have to look inside of it to see how is it built. Okay, and this is part of why I show you how these things are built. This is a 6 LUT, okay? A 6 LUT is, I'm actually showing there's a 4 LUT, a 4 LUT, a 4 LUT, a 4 LUT, because there are 4 input lookup tables inside a 6 LUT. We then have a multiplexer that chooses between the outputs of these two, and another multiplexer here that chooses between the outputs of these two 4 LUTs. Okay, so that's a 5 LUT, right? And then if I take these two outputs, here and here, and I add one more multiplexer and choose between them with another input, that's a 6 LUT. Okay, so what I've just drawn here is a structure that is a 6 LUT. If I draw a box around this whole thing, that's a 6 LUT, and that's my 6 LUT output. But it also can do 2 5 LUTs, and it also is 4 4 LUTs. Okay? So hopefully you can see all that. Does that make sense? And let's see. Everything, okay, so if I take this 6 LUT output and I draw all this, all of that I need to make a 6 LUT, right? It's all going to be in there. So it seems like it's a free lunch, right? Everything I just circled is in a 6 LUT already, and if I just am a little more clever about my inputs and outputs, I can use this in all sorts of different ways, and it's going to be great. And so the Stratix 2 paper calls this a composable 6 LUT. So what do you think? Do you like this? Isidore, what do you think? You like it? Yes. So if I only look at the circuitry that's inside the logic element, it looks good. I didn't add much. But if I count routing ports, it's enormous, right? A 6 LUT has 6 inputs and 1 output. This has 19 inputs and 7 outputs. So I'm going to have to pause to count it. Okay, so it's got a huge amount more routing ports. And we saw that routing ports are not like a second order issue. These are big. So this thing actually looks fine. If you only think about the logic element, as soon as you add the routing ports, you say this thing is enormous. Do not build this. Okay, so the alternative that they came up with is a fracturable LUT. So here's my 6 LUT again, right? It's built with 2 5 LUTs and a multiplexer. So I get my 6 LUT. And it fundamentally does have 2 5 LUTs in it. But they want to expose some of that functionality of those 2 5 LUTs without adding many or any routing ports. So the minimum I can do is basically add 1 extra output. If I just say that this bottom 5 LUT, it used to only go into this last mux. If I say it also goes out to the general routing, okay, I added 1 output routing port, which is something, but it's not too bad. And now I can use this whole thing as a single 6 LUT here, or I can use it as let's see, can I use it as, yeah, I can use it as 2 5 LUTs. I basically have to set this signal to 0. If this is my 0 input and this is my 1. And now I get 1 5 input function coming out here. and I get another 5 input function coming out on my new output. Okay, so it's much more area efficient. What have I lost? So I did lose something when I did this. It's not free. What did it cost me? So let's see. So I'm going to go to Isidore in a second, but anybody else want to come in here? Go to Alex in a sec. George, what do you think? So I've saved input ports, which is good, but what have I lost by doing that?
Yeah, so that now you can't support as many like inputs.
Yeah, so I have a significant restriction here. I can use this as two 5-input lookup tables, but together they can't use more than 5 inputs. Okay, now because I actually had a lot of like 3-input and 2-input lookup tables in that chart I showed you, that's actually still useful, right? I can actually take those 3-input and 2-input functions, and for sure I can put a 2-input function here and a 3-input function there. That's good. Also, it turns out that if I have, for example, 4-input functions and 5-input functions, they often share some of their inputs. So I can get some reasonable use of these two 5-LUTs, even though I put this restriction on them of they have to share all of their inputs. Oh, I even wrote it on the slide. Good. This is actually okay, so the fracturable LUT was first done by Altera. And I told you that you can tell something is kind of broadly adopted when, like, if Intel does it and then AMD copies it, or AMD does it and Intel copies it, usually now it's there to stay. So a couple generations after Altera did this, Xilinx also adopted fracturable LUTs. This is the fracturable LUT that Xilinx adopted. So they chose to do a fracturable LUT with essentially minimum cost. They're like, what's the least thing we can add to a 6-LUT to be able to use it as two 5-LUTs? And the least thing you can add is one extra output port. And that's exactly what they did, okay? But they have this significant restriction of no more than 5 distinct inputs. Yeah?
Is this not something with the patents?
That's a good question. Yeah, we did patent the heck out of this. So I'm on some of the patents for that. You can come to my office, you can see some of the plaques. I got paid for them, et cetera, right? So let's see. So they're probably hard to design around, so this probably does infringe an Altera patent. I mean, I haven't gone, but when I was at Altera, we actually encouraged not to read Xilinx patents, and they probably had the same rule. The reason is if you actually knowingly infringe somebody's patents, it's triple damages. So there's so many patents out there by your competitors and so on that basically decisions made is just better don't look at them. We don't want you getting ideas from them, and frankly, if you came up with the same idea independently, we don't want triple damages. So it probably does violate them. They would try to design around it. They'd try to, like, theirs is different, so they'll try to go around if the patent isn't broad enough, and maybe they were able to. If the patents were broad enough, then they wouldn't. When I first joined Altera, everybody in the FPGA industry was madly suing each other for patent infringement. So Altera was suing Xilinx, Xilinx was suing, well, Xilinx sued Altera, Altera sued Xilinx back. I think we had a lawsuit going with Lattice as well. So we were spending $20 million a year on litigation. And we believe Xilinx was spending more because they were bigger, so they could. And that ended in the tech crash after 2000. And it basically ended because the CEOs of the various FPGA companies went, we're cutting costs, we can't afford to litigate against each other so much. And essentially, everybody infringed somebody else's patent somewhere. So Xilinx and Altera basically just sat down, compared the height of their patent portfolios, and said, okay, we're settling. And Xilinx's patent portfolio was like, I don't know, some amount higher than the Altera ones. They said, like, pay us some amount of money, which was maybe $10 million, but it's less than the yearly litigation. And then was settled, and we cross-licensed all our patents to that date, and we agreed not to sue each other for at least 5 years. So like for 5 years, they just literally couldn't sue each other over it. But it's also, against like a strong competitor, it's not really in your best interest to sue them for patent litigation, because you probably both infringe each other. So you will just give a whole whack of money to a bunch of lawyers, and in the end, you will just cut a deal. So you might as well just cut the deal. Does that make sense? So, yeah.
So it's kind of like if I owed you $20, but you owed a Min $20, and Min owed me $20, they just kind of all came together and just settled it. Is that what they did?
I guess it's sort of like, it was basically like the litigation is not going to result in a clean outcome where like you win and I lose. It's going to wind up with like we each win some, lose some, but we're going to pay a whole pile of, we are paying a ton of legal fees. So in the end, we might as well just come to an agreement right now. I don't, like from the Altera CEO, like even paying them some amount of money, like $10 million or something, was more of like a, the Xilinx CEO was like, my style of patents is higher than yours. I feel good about my chances. You got to give me something, right? Because for both companies, like $10 million is not actually very significant compared to their yearly revenues. So that amount of money is basically kind of just, I gave you like an award saying you win. Do you know what I mean? Like Alex, you are smarter than me, right? Here's your certificate, right? so, so. The litigation is funny. It's interesting. So if he wants in the break, I'll tell you more litigation stories. Yeah. Well, I mean, it is a fancy way to pack more LUTs, but it's very efficient. It's very efficient because we're basically breaking up circuitry that's already there. And this is a common thing in FPGAs because you're trying to make them programmable but as efficient as you can. Can you find some place you can add more programmability that's really cheap? And if you can, and your tools use that a significant amount of time, it's a win. So fracturable LUTs were one of those ways. Like you look inside the LUT, and if we make this small change, we can use it in two different ways, and the tools would like to use it in both ways, so it's a good change. But you got to keep it cheap. Adding all these routing ports was not a good idea. You got to not spend so much. Yeah.
And the hard-coded zero that's used in the routing network, the way we talk about it now, is there a fast path onto the routing network with ground and PC?
So it doesn't have to be fast, but the routing networks and FPGAs the routing muxes and FPGAs normally have one input that is ground. So this Xilinx could do for free, right? This is a routing port, connecting to ground is easy. The reason the routing muxes have a ground input is you have a bunch of routing wires that you're not going to use. You know, your design doesn't use them, they're not connected to anything. You can't leave those floating, okay? Leaving nodes floating in a circuit is really dangerous because what if they float to VDD over 2 and they're connected to an inverter, which typically happens. They're connected to something. You don't really care what they're connected to from a functionality point of view. You're like, I'm not using that wire. But you do care if it drifts to VDD over 2 and it's connected to some inverters and start leaking like crazy. And you now did that 100 million times, your chip melts. So the routing muxes normally have one input to ground that the CAD tools can use, which means this is also just free. Does that make sense? Okay, so I just showed you what Xilinx did. They actually did it a bit after this, and they did it a bit different. What did Stratix 2 do? Stratix 2 basically said, well, we are building a 6 LUT, and a 6 LUT, that's this. Okay, so this shows 4 LUTs, which together can be grouped into 2 5 LUTs. So that's what I'm showing here. And those outputs can be grouped together into a single 6 LUT. They added a bit more than Xilinx did. So I'm not going to go through all the details of it, but basically they put 8 inputs in, not 6. And what that allowed them to do is you can use this as one 6 LUT or 2 5 LUTs. If you use it as 2 5 LUTs, together they can use up to 8 inputs. Okay, so that means you could always do 2 4 input lookup tables for sure, and you could do 2 5 input lookup tables if they share 2 inputs. And it turns out those are pretty common. On the other hand, routing ports are expensive, so adding 2 routing ports is not an overwhelming cost, but it's not free. It is noticeable. So when after Xilinx shipped their parts with fracturable LUTs, we did an analysis of their area and the synthesis results, and we actually concluded it was about a tie. Okay, they were able to fit more of their fracturable lookup tables into a unit of silicon area, but they also did need more of them to map the average circuit, and the two effects were mostly, to first order, canceled out. So that both of these logic elements appear to be about roughly equal efficiency, but just coming at it from different points of view. Let's see, I think I've talked about all of this. Basically, yeah, I mean, this is just another way of saying that, well, most of our LUTs use 5 or fewer inputs, and a 6 LUT does actually have a truth table and the muxing structure inside of it that is big enough for 2 5 LUTs. So if we can expose that, which fractural LUTs do, we can use that sometimes. And yeah, Altera decided that 8 inputs was the best. Xilinx decided that 6 inputs was the best. They're kind of both right. There's a broad minimum. What does this do compared to the usual non-fracturable 4 LUT that was dominant before that? it made the design, the FPGA 15% faster, which is a big win for one change, right? It's actually hard to make your logic fabric that much faster without a process change. And it actually saved 3% area. So the fracturable, some things fit very efficiently in a 6-LUT. There can be some logic structures that take a lot of 4-LUTs that actually fit into one 6-LUT. So sometimes you get an area win from a 6-LUT as well. This ability now to use different sizes of LUTs actually resulted in the fracturable 6-LUT having a better area as well. So this is now a pretty significant area delay win, whereas Ahmed and Rose, where they were comparing 4-LUT and 6-LUT, they were kind of even in area delay because the 6-LUT was 17% bigger. So Altera was able to get the speed win without the area bloat. That was the impact of this. And it's basically been adopted by at least most of the industry. And this is just showing, well, if I map to that, what can I do? So I can obviously do a 6-LUT. I could do 2 4-LUTs. I could do 5-LUT and a 4-LUT as long as they share one input and so on. Altera also did a very tricky thing that's in that paper where they said, well, I don't have a big enough SRAM, big enough truth table to do 2 6-LUTs, but I could do 2 6-LUTs if they are the same function and they actually share 4 inputs. And that sounds useless. You go like, well, when are you going to get that? But it turns out that multiplexers and crossbars are very common in FPGA designs. They're not just common in the architecture, also common in what people use in their designs. And you can use this to build a crossbar in somebody's design. Now it did actually take a few percent of area, so they took it out again in Stratix 10. So this was something that went into Stratix 2. It was maybe a little too clever, right? Can be used sometimes, but adds a little bit of area. So they decided in Stratix 10 it was more bother than it was worth. So that complicated one you can ignore because it doesn't exist anymore, but all the other ones still do. Okay? Xilinx has like a similar chart of what they can do, but they need more sharing of inputs because they didn't build those 2 extra input ports. Okay, and I think I'm going to stop there for a break. Why don't we stop till 5:45? Okay? Sorry? Probably the next Okay, so we're going again. So let's see. So actually, once you make a big architecture change like this was a major architecture change, you go look at your tools. So this is actually additional results from the Cordis synthesis tool. Basically, once you have this fracturable 6-LUT structure, the synthesis tools, you can just have them map everything they can to 6-LUTs. That's what Cordis calls speed synthesis. That's what we would have had in the previous chart where we just said map everything to 6-LUTs that you can. So you get, here we're getting maybe 20% or 20-some% map to 6-LUTs, another 20% to 5-LUTs, and 20% to 4-LUTs, and other things are smaller. But there's now a benefit if we don't need it. We don't think we need it in order to get a particularly efficient mapping where this 6-LUT, we'd need to use 3 4-LUTs, for example, or 2 4-LUTs to replace it. And it's not on the critical path. Like it's not going to reduce the maximum depth number of LUTs in series. The Cordis synthesis tool will say, well, 6-LUTs are actually now more expensive than 4-LUTs and 5-LUTs because I might be able to pack 2 4-LUTs or 5-LUTs together, but I can't really pack 6-LUTs together. So now we've got an additional area optimization. It'll tell the synthesis tool, don't use 6-LUTs if you don't need to, because 5-LUTs and 4-LUTs, basically the synthesis tool has a cost function, and you tell it 5-LUTs and 4-LUTs are a bit cheaper. So if you didn't need it for speed reasons, this is not a speed critical part of the circuit, and it wasn't particularly efficient to use a 6-LUT, then go use one of these. So when we do that, you get more 5-LUTs and more 4-LUTs, which improve the efficiency still a bit more of the fracturable 6-LUT. And that's basically the way that both commercial and academic mappers to fracturable LUTs work now too. So ABC, that open source tool from Berkeley that I showed you in the VTR flow, it also does this, right? It understands that smaller LUTs are cheaper for this kind of architecture. Okay, so one of the other things that had to happen for Stratix 2 and Stratix 3, which has a similar architecture, is to pick the size of the logic block. Okay, so we've changed the lookup table structure to this fracturable 6-LUT. Now we need to choose how many of them go into a logic cluster. So Ahmed and Rose said 4 to 10 was pretty good. And this is the result from the Stratix 2 paper. They basically did architecture experiments with a very n, the number of these basic logic elements or fracturable 6-LUTs in a cluster. And they varied I, the number of inputs to a logic cluster, so Altera calls those number of ALMs per lab and the number of lab lines, but they mean N and I. And they found the best answer was at N equals 10. But 8 and 12 weren't bad either. Okay, so it's the best answer in that it got the lowest area and it got the a good frequency. So the best area delay trade-off was basically at a cluster size of 10. Somewhat inexplicably, for Stratix 2, they went with 8 anyway. But in Stratix 3, went with 10, which the architecture data in the paper says they should have gone with for Stratix 2. So as I said, I was actually around for this whole exercise, and I actually don't remember why we would have chosen. Maybe we couldn't read the table properly, and we needed another generation to go, oops, it turns out the line below is actually better. But Stratix 3 is easy to explain. Took the best row in the graph. Let me ask you a couple of questions about this. I guess one trend is logic blocks are slowly getting bigger. Okay, so if I go back to older FPGAs, really old ones, single lookup tables, then 2 lookup tables and 3 lookup tables in the logic block. Stratix 2 has 8, Stratix 3 has 10. So the logic blocks are slowly getting bigger. Yeah.
Make a lot of sense in that bigger progression. I mean, you usually want to be, conservative as you're doing things. And if you're already using small blocks that you know work, you may want to say, well, we're not going to increase it super big.
Maybe. I mean, there could be layout reasons too, like you're trying to pitch match this. So there can be detailed reasons. There are, and I'm being somewhat facetious, so maybe we couldn't read the table, but Altera's chief FPGA architect was David Lewis for many years. He reported to me, right, also for many years. And Dave was formerly a prof here at U of T, okay, so he left to join my startup and then joined Altera. And so despite being a prof, his favorite plot looked like this, okay? that is complete. Okay, there's nothing missing from that plot. He would bring those kind of plots to architecture meetings all the time. And I'd say, Dave, what's the x-axis? What's the y-axis? And then he'd say, well, it's obviously this. It's obviously that. It's like, so I'm supposed to infer that from the shape of the curve? So there's a non-zero possibility. He just didn't label some data. and we put the wrong thing in. So anyway, don't do that. So there's this trend of logic blocks slowly getting bigger. Let's see if like that, remember the Almond and Rose study? They said they found this empirical answer that when they looked at how many inputs do they need to this kind of logic block so the CAD tools could use all the logic, they needed about half of the maximum, right? They came up with this equation, k over 2 times n plus 1, which is about half the inputs on the lookup tables should be exposed on the logic block. Okay, so does this agree with the Stratix n equals 10 values? Okay, so here's Stratix 3, n equals 10, and they said that their CAD tools said that 46 was a pretty good number. Okay, so if I take 6 LUT, okay, so k equals 6, n equals 10, and I just plug those numbers into this, I get I equals 33. So I need 33 inputs, but they actually said in their architecture experiments that 46 was a good value. So does this mean that equation that I just showed you is without merit? Or Altera misread another Dave Lewis result because it wasn't labeled? What do you think? Can these things be reconciled? So they can actually. So if they couldn't be, it's a less interesting question. So you can actually reconcile this. How do I reconcile these two results? I could do that. I could just do some kind of mathematical heuristic operation, right? So there's the deep learning method, and I'll just put it through another layer and see if it comes out correct after that. But as Jeff Hinton said, maybe you've had too many more layers and it'll start telling you what to do. So is this the only way we can use this logic block? So this says it has 10 6 LUTs in it. Okay? What else does this logic block do? So it's a fracturable 6 LUT. So this is not the only way I can use that logic block. I can also use it as 25 LUTs. Okay? And I will use it as 25 LUTs sometimes. And I'll use it as sort of combinations sometimes too. But if I just rerun this equation with 25 LUTs, I actually get 52.5. 25 LUTs just are going to use more inputs. Okay? So that's actually going to stress the input bandwidth of the cluster more. And that's actually what set this limit. So actually in the paper, while they showed this architecture result and said architecture showed 46 was good, this is where they did get a little conservative and say, you know what, let's add a little margin, let's do 52. Okay? And that 52 is very close to what Almond and Rose would have predicted, but only if you realized you have to apply their equation like for all the ways you can use this logic block. And the two extreme cases are all 6 LUT and all 5 LUT. And the all 5 LUT is going to produce more input signals. So we want to watch for that one. Make sense? Everybody with me so far? Okay. Okay, so another question you have to make is how many flip-flops do you put in for this fracturable 6 LUT, which Altera calls an ALM, or adaptive logic module. So far we've always had like a LUT and then a flip-flop. Now we basically said we've got a 6 LUT, but also it could be broken into 2 5 LUTs. So should we have 1 flip-flop or 2? What do you think? Yeah.
I think we should be putting our flip-flops in the routing last place, and then we don't need the 3 LUTs.
You're reading way too far ahead. So for those who don't know, that's going forward to like another architecture change that we'll get to in a few weeks, which has not been universally adopted, which also means it's not clear when you have different companies make different choices, you go, maybe a good idea, maybe not. So that one's more unclear. Okay, but ignoring that, what do you think? Should I put 1 register in here or 2? Well, how expensive do you think a register is? I mean, I haven't drawn the circuitry inside a register, but how big do you think it is? They're pretty cheap, right? You've got two latches, a master and a slave. They're both cross-coupled, so you've got cross-coupled inverters with some control. So they're not that expensive. And compared to what's in a lookup table, they're pretty small. Compared to like these routing ports, they're pretty small. So Another register is not too expensive. So that maybe is part of the story. Another part is how much do people like pipelining? And are they doing more pipelining or less over time? Yes. Maybe you're tired of pipelining by now, right? But in general, designers love to pipeline. So if you're tired after assignment 2, well, it's okay. You'll recover and want to pipeline again within a week or two. So yeah, they like to pipeline, and pipelining is getting deeper over time. So there is a trend for FPGA designs to get more register rich. So if we only had one register, we essentially would have made the architecture more register poor. Before, we could register after every LUT, and now we'd only be able to do that for 6 LUTs, and 5 LUTs we couldn't. So yeah, the better choice is don't do 1 register per 6 LUT, do 1 per 5 LUT. Yeah?
Or we could do both, and then we can have 2 output ports, one that goes through and one that doesn't, just so that we get the fast path.
True. So yeah, we actually did this experiment. 1 register per 6 LUT leads to register starvation for a lot of designs. You really want to put in 2 registers anyway. And the cost to add another register is small, as long as we don't add routing ports. If you actually basically put another register in and you give it independent routing ports, then that's actually considerably more expensive than a register. So what did Stratix 2 do? And later Altera Intel chips look pretty similar to this. So they put 2 registers in, so 1 after each 5 LUT. So use a 6 LUT, you can register it. Use 2 5 LUTs, you can register them both. Didn't add any extra routing ports, so still at 8. What was done instead is they added 2 small muxes, a 2-to-1 mux here. Okay, so there's a 2-to-1 mux here that basically allows you to take a signal from either a routing port or from the LUT. And so both of these registers have that 2-to-1 mux. And there's a 2-to-1 mux in front of the LUT that basically allows it to take a signal from either the routing port or from the output of the flip-flop. Okay? So I probably should draw this better. It's basically like a little trick. Like these routing ports are relatively big muxes. It's very common to have a LUT and you want to register its output. So you want to be able to do that for sure. If I want to be able to use this register independently, I need to basically bring a signal in on a routing port and go in instead. To enable that, I just need a 2-to-1 mux, right? Take the output of the LUT or take this routing port. Now, I didn't build any more routing ports. I only have 8. So every time I do this, I'm grabbing one of my scarce routing ports. It's going to be harder to use my LUTs. So Altera did another trick of basically sometimes you have a register and it's feeding back into the same logic element. So you can basically put a 2-to-1 mux in front of one of your LUT inputs, and you can either take a signal from a routing port like usual or take it from the output of the register. This basically gives you options of how can I combine the LUT and the register in more combinations with several of them not requiring a new routing port. And it's all to be able to make use of both these registers, even though I only have 8 routing ports that have to be shared between the LUT and the flip-flop. And I don't think I'm going to talk about the rest of this. So, okay, and this FPGAs keep getting more register rich. Okay, so Stratix 5 and beyond. So if you want to read it, there's an interesting paper on Stratix 5, but I'm not going to assign it because there's just too many papers to read otherwise. But Stratix 5, Altera made another change of they went from 2 registers per ALM, which is what I've shown here, to 4 registers. But they still only have 8 routing ports. So now they've got 2 LUTs and 4 registers. The LUTs can feed the registers can feed the LUTs, so there's some little bit of internal connectivity. But you can get a fair amount of competition for these routing ports. So when you use all 4 of these registers, well, you need really small LUTs or to leave the LUTs alone. It's still a win, but it does get a little more challenging for the CAD tools to use them. Okay, and then I'm following along on Intel's architecture evolution. So another change came in Agilex, which is their most recent FPGA in 10 nanometers. So this isn't a change in how much of stuff they have. They still have 10 ALMs or 10 fracturable LUTs. Still, You know, six input LUT with 8 inputs, could be broken into 2 4 inputs, still has 4 registers. What they changed is the local routing. So all the Altera parts up until this, or Intel parts up to this point, had the local routing structure that I've shown you. Of basically, you have these local routing wires that are essentially the whole height of the logic block, and you have I signals from outside that can feed into them, and you also have signals within the logic block and feed back to them. Okay, so you have that kind of sort of simple structure of interconnect within it. With Agilex, they found that these wires that go the whole height of a lab or logic block, even though they're not that big, it's a single logic block, they're starting to get noticeable delay, like more delay than they want. So they basically added another level of essentially routing hierarchy. So these 4 kind of quarter height symbols are indicating even smaller wires. So in Agilex, they divided their local routing into 2 groups. There's a group that only spans a quarter of the logic block. So it basically connects 3 of their fracturable LUTs. And they repeat that for each group. And then they have some other ones that are more the traditional, it can reach all of the ALMs. Okay, so their local interconnect got more complicated in Agilex. I kind of mentioned this when we were talking about hierarchy. It's kind of like they've got like 2 levels of hierarchy inside of the logic block interconnect now. And it's done because, metal delay is not scaling well. So the metal R continues to go up, and that means that long wires, even the entire height of a lab, don't scale and delay very well. And the way they're dealing with that is saying, fine, we'll make even inside the logic block some of the wires shorter. Does that make sense? Okay. Well, and this will be one of the papers that we read later on. There are a bunch of new things in Agilex. This is one that relates to logic blocks, but not the only thing. So let's talk a bit about Xilinx. So I talked a bunch about Intel's FPGAs and logic blocks. How does Xilinx the same or different? So part of this, I guess I already talked about. They adopted fracturable LUTs as well over several generations of their product. But basically, I told you they did it to keep the logic element as cheap as possible. They didn't build extra inputs. So for several generations, they could use a total of 5 inputs for when they used 5 LUT modes. They had either a 6 LUT, which could use all 6 inputs, or they had 2 5 LUTs, but together they could only use 5 inputs. They eventually, in Versal, their most recent chip, they relaxed that a little bit. So now when you use 2 5 LUTs, you can use 6 inputs. What did they do to make that happen? They basically didn't have to add very much. Let's see if I see it in here. I'm seeing if I drew that on here or not. So, yeah, I don't think I drew it in here very well. So I have to draw that afterwards. But they make a very small change that allows them to basically use this 6th input, which they were already bringing in anyway. They don't have quite as many flip-flops. So recent Altera or Intel chips have 4 flip-flops for each of these logic elements. They only have 2. But Xilinx basically has a routing port that goes directly to the register. Okay, so they have this extra routing port, and it can feed through these little muxes, into either one of their 2 registers. And then the other one has to be fed by one of the lookup tables. So while they have fewer registers, they're actually a bit easier to use, right? Because they put in a dedicated routing port that you can use as well as just taking the output of the LUT. This is also probably a bit easier for late CAD optimizations. So because the legality rules are kind of more complicated in the Intel ALM, when we architected it, we thought this was very clever, and it fit our CAD flow well, where we basically pack things together into logic blocks, or at that time anyway, we packed things together into logic blocks and then chose where to put them. We could deal with legality constraints pretty well in that. Xilinx doesn't seem to like complicated legality constraints as much, And what this allows them to do is late in their CAD flow, when they're fine-tuning their placement, it's easier for them to take a register from one logic block and move it to another one, and it's more likely it's legal. Because they can always use this extra routing port to get at the register. So that might be a good choice, because their registers are probably easier to move late in the CAD flow, whereas Intel flows might have more trouble. We'll also read this paper later on, but Versal is Xilinx's most recent chip, their 10 nanometer FPGA. And their logic block, again, is fracturable LUTs. And they've gone in Versal to a very large logic block, 32. So it's interesting. Intel basically said a logic block with 10 things in it, the local interconnect is getting slow enough, we're going to start splitting some of the wires into multiple pieces. Xilinx basically, in their paper, say we want to capture more connections on the local routing. So the blue is showing what fraction of the local connections in the whole design could they capture on the local routing in ultrascale, their previous generation. And by basically making the logic cluster bigger and making the local interconnect more flexible, they said, well, we can capture a lot more. So we can capture about 15% of the connections can now be made with our local routing. So they're kind of going in somewhat opposite directions. Intel is making its local routing a bit more complicated, and Xilinx is making their logic block bigger and making their local routing a bit more flexible. So it is interesting. While they're both facing the same technology trends, how they're dealing with them are somewhat different. Okay, so that's it for the slides on this. I know there's a lot of information. You will read a couple papers on Agilex and Versal where you'll see more of this, but these parts relate to the logic block. Any questions on any of that? Okay, so in that case, I'm going to switch to the chalkboard for a little while. And we'll talk about something related, but a little bit different. So let's turn off the projector. All right, you guys look sleepy. I'm going to tell you one more patent story in the hope of waking you up. So yeah, I told you about Xilinx and Altera suing each other, eventually settling. Another lawsuit that happened was that Altera was a much smaller company called, I believe it was Atmel. Atmel makes a bunch of stuff like microcontrollers and so on, but they also made like some small programmable logic parts. And somewhat inexplicably, they decided to sue Altera over violating a patent on some muck structure in interconnect. And because they weren't like a major competitor, right? Like Altera made big chips, Atmel made some very small ones, but I guess someone in Atmel just decided this would be a good idea the way to make some money. So they sued Altera, and I heard about it because when these things happen, they tell engineering, like, what do you think of this, and so on. They call a few people in to look at the patent. And they sued in California, and it takes a while for lawsuits to go through. So Altera's lawyers went through their patent portfolio and they found something that Atmel infringed. I don't remember what it was. So they countersued, which is again standard, like you have companies that have big patent portfolios, is part of why they have it. So anybody who sues them, they can countersue. So they countersued over something that Atmel violated. But Altera's lawyers were better because they didn't sue in California, they sued in East Texas because they know East Texas basically runs cases much faster. So the patent case in East Texas was heard before the one in California. Atmel lost, and basically I forget if they were given an injunction where they couldn't sell the parts or not, but or if they were just directly ordered to pay damages. But they basically had to pay Altera damages, and as part of not going further with it, they agreed to drop their lawsuit. So anyway, it was interesting. If you're going to engage in patent litigation, you want to have actually very good lawyers, because I was thinking whoever started this lawsuit at Atmel is going to have a really bad yearly review, right? Like I decided to file this lawsuit for no apparent reason. I thought I'd make some money. Now I've actually cost the company a bunch of money because we got sued and lost the lawsuit. So yeah, it was kind of inexplicable. Okay, so let's talk a bit about, okay, so we've been talking about logic blocks, and we can build anything out of them. They can basically build anything we want, and they're basically bit wide. Okay, so we can do bit by bit wide, I mean we have control over every single 1-bit value that goes into the LUT inputs and into the flip-flop data inputs, and they have word-wide control for the flip-flops. Okay, so flip-flops usually share a clock or maybe 2 clocks. They share a clock enables and so on. So they work pretty well for those things. Okay, another very common structure in circuits is arithmetic. Okay, so let's say I want to do this. Okay, so sum becomes A plus B, and let's say they're all 32 bits. Okay, so all I'm doing is a 32-bit add of A and B, storing the result in sum. Okay, what does this look like? So, hopefully this is not a hard question. How do I do this in LUTs? I can't do anything. I can do this in LUTs. Yeah. Yeah, so I'm going to make a bunch of full adders. Okay, so let's just draw that out to show what it looks like a bit. So I've got A of 0 and B of 0, because I do have to do it bit by bit, right? A LUT is, well, it can't do all 32 bits. Okay, so I take these two in, and I can produce sum of 0. You're going to come up with a more efficient solution, but I'm doing 4 LUTs. Are you doing 6 LUTs in your head? Yeah, I'm doing 4 LUTs, so it's simpler. But you are right. For 6 LUTs, you can actually do this slightly more efficiently. So, okay, so that's the sum. Okay, I also need to compute a carry. So I'm going to do that carry in another way. Okay, so this is my C out of 0. And that gets my repeating structure now. So the C out of 0 is going to go into my next LUT, which also has to have the next bit of A and the next bit of B, and that produces my sum. Okay, so this is my next sum bit. And I need another LUT to produce my carry for that as well. Okay, so let's see. So I need to send that in there, and I need to send okay, so the basic structure is the repeating structure is I need a LUT to compute each bit of the sum, and I need another LUT to compute the carry out. Okay, and I can repeat that over and over again. So for a 32-bit adder, how many LUTs do I need? And I'm doing 4 LUTs. Okay, so I do 6 LUTs. Some of these things divide by 2, but everything's more complicated to draw. So none of the conclusions change. So this is not a super hard question. I'm going to check if anyone is still awake. 32-bit adder, how many LUTs do I need with this structure? Yeah, so I need 64 LUTs. Yeah, that might be true. Okay, so I'm going with 64. I like your answer. You're right. If I don't use the last carry, I could avoid building it. And I think Isidore, you're also saying that these are 4 LUTs, so technically this first carry you could actually just pack in here and get rid of this one, right? Because it would. So you're right. So we could maybe do it in 62. Okay. So we'll go 64 LUTs. Okay, that's the best solution. Okay, and 62 LUTs class. Okay. So I'll acknowledge that the class has cut 2 LUTs off the total, but the repeating pattern is still there. Okay. So that's a reasonable amount of LUTs for a 32-bit adder. And most of them are only using 3 of their inputs, so it's also a bit wasteful. What about the critical path? Okay, yeah. How low can this go? What?
If you take like a 5 LUT, for instance, and you pack it.
No 5 LUTs. I'm only doing 4 LUTs.
Okay, A0, B0, A1, B1, and then 1 carry bit, and then you make 2 of those 5 LUTs. You can pack that potentially more densely.
Boy, I don't have 5 LUTs. You're just saying visualize the 5 LUT as a weighted map this?
No, you have 5 LUTs.
I've only got 4 LUTs. I'm already like 2 LUTs behind the class, but I've only got 4 LUTs. If I give you guys 5 and 6 LUTs, I don't know where this is going to end. Right? The mapping is going to get too complicated for me. So, okay, let's talk about the critical path. So we don't really know the critical path of a design until place and route, but we can estimate it just from logic levels. That's how many LUTs we need, that in series, how many routing hops. So estimating the critical path, how many LUTs are on the critical path? And it's going to be that many, at least local routing hops. 32, yeah. So we have 32 LUTs on the critical path, which sounds pretty bad, because all I'm doing is a 32-bit add. It's going to be that's not a lot of work. Okay, so I'm going to put an exclamation mark, because that concerns me. Okay, so I'm coming back to you in a second. So let's just take an estimate of how, we haven't done place and route, I haven't told you what chip. I'm going to estimate that the delay through a LUT plus the interconnect after it averages, say, 500 picoseconds. Okay, and you could argue, oh, maybe it's 300 picoseconds. I got a faster chip. Doesn't matter. Okay, so let's say it's 500 picoseconds per LUT plus the interconnect. The LUT itself will be less than 500, but I got some routing after it. Okay, so for a 32-bit adder, that means I got 16 nanoseconds on my critical path, which implies an amazing operating frequency of 62.5 megahertz. And that's just to do a 32-bit add, right? I didn't do anything else in the whole clock cycle. If I wanted to add this to another number or use a mux or something, it's going to get worse. If I want, God help me if I need to do a 64-bit add, right? So I could pipeline this. Yeah, okay, so that's my next question. So let's say I gave you, what can I do to make this better? So this is going to be a problem. Adders are common. So in a typical, it varies a lot, but a typical, over many designs, you find that about 15 to 20% of your logic is arithmetic. Okay, so that's a lot, just doing addition and subtraction. If you build multipliers in your logic fabric, so you run out of DSP blocks, you start building multipliers, they're built out of a bunch of shifters and adders. So that's part of where that comes from, and then it turns out addition is just common everywhere. If you're doing, so that's the average across kind of all FPGA designs. If you're in a signal processing design, it's a lot higher. If you're in something that's doing packet switching, it's somewhat lower. But it's a lot, okay? It's not a rare thing. So we're going to have a lot of really problematic critical paths. So what are we going to do about this? And actually, before I do that, looking at my notes, I'm like, this is a good idea. I should do this. Okay, let's see if this is just bad for LUTs everywhere. Okay, because maybe adders are not special. Maybe just LUTs are terrible. And we should cancel the course, right? So because we're so far in now, we're in trouble. So let's just compare this to a 32-bit AND. Okay, so out is A and B. Okay, and it's again 32 bits. So the structure of this is basically more parallel. Okay, so I've got A of 0 and B of 0. I put that into a LUT, and I get output of 0. And that happens on every single, bit level. So all the way down at A31 and B of 31, I get the same structure. Get a lookup table, and I get out of 31. Okay, so number of LUTs is 32. So it's half the size, so it's smaller. It only uses 2 inputs each. Okay, so it sounds better from an area point of view, not using the whole LUT, only using half as many. It's actually easier to pack stuff in with this. So there's logic before this, logic after this. I use 2 of my inputs. I can almost certainly pack some more stuff in here. Okay, so it's easy to pack. More logic in. Okay, so for example, if I was doing A and B, which is what I just did, and then I said or C and D, all 32 bits wide, I could get the or C and D in here, no extra LUTs. That's not so true with this carry. This is way down. It's harder to pack stuff in here. I guess I'm already using 3 of the inputs, so that's one reason. And I guess I might be able to pack something else out here, but if it was another adder, it's not going to pack in very well. If it was something very simple, I might be able to pack it in. So this is easier to pack things in. But the big difference, so there's some difference in area, right? General logic like this is more area efficient than what I found for the adder. What's the critical path of this? Right, so critical path, this is 1 LUT or 500 picoseconds. Yeah, my 500 picoseconds includes routing. So it's 1 LUT plus routing. So it's about 500 picoseconds. Okay, so that's going to limit me to 2 gigahertz. Now, realistically, I'm not getting 2 gigahertz, but it means that, yeah, I can do some more stuff after this. I'm not out of my clock cycle. Whereas here, I'm like already well beyond probably what I want as a clock cycle. And all I did was an adder. So what's annoying about this adder structure is it's common, and the serial carry is killing me in terms of delay. Now, Isidore, I think you basically had an idea of what to do about this. So what do I do about this?
What you can do as someone writes Verilog, there's more complicated adder structures you can do that may do some look ahead and make things a little better.
Yeah, so let's stop with that for a second. So if this is my architecture, then that's what you would do. This is a ripple carry adder. It's actually still taking a lot of LUTs, but it's area efficient. The logic in a ripple carry adder is relatively simple. There's a whole huge literature on actually adder designs. Arithmetic's so common in just every kind of chip that you will never count all the papers about different ways you can build adders. Okay? And some of them basically do what are called parallel prefix computations, where they essentially take a bunch of these, they get rid of a bunch of the rippling and essentially compute some of your later carries by throwing more logic at it. So they reduce the logic depth, and they pre-calculate some of the later carries. That's the basic idea. There's a million ways to do it, but you will speed things up by doing that. What are you going to pay? Yeah, your area will get worse. Your delay will get better. It's still not going to be 1 LUT, but you could reduce it to several LUTs at the cost of several times more area. Could do, if that's all we had in the chip, then every FPGA designer would be doing this, right? You'd be off studying how do I make parallel prefix adders, and you'd be an expert in it. But we can change the chip. So if we change the chip, what can we do? Yeah, so we want to do better. Okay, this is common, so in my notes I wrote down 10 to 30% of logic typically, so we don't want to make designers do expensive, complicated things that are still not going to be as good. So we want to do better in the architecture. That's true. Cordis would do it, but the designer would still see the output. It would be annoying. So, and Cordis would be dealing with kind of still a nasty trade-off space. How much area do I spend for how much delay, and I'm still unhappy with the results.
I mean, that already is the recommendation. It's just the pipeline registers everywhere, and that's where it's good.
So you're right. If we couldn't do better, we'd tell people to do that, but they will be unhappy. So we're going to try to do better than that. Okay, so when the general logic fabric's not efficient enough, right, we can build a special block. So that's first thing we should probably think of, or often think of, is can I build a special block for this? Okay, so here's my special block. I'm going to build hardened adders. Okay, so I'm going to have logic blocks, RAM blocks, DSP blocks, and adder blocks. Okay, so what does my adder block look like? Well, it just looks like a bunch of adders, ripple carry adders, or maybe I want it even faster. I harden some carry look-ahead adder structure or something. And it produces, a sum output. And it takes in A and B. And they're both multi-bit. Okay, so this one I just did 4 bits, but probably I'd make it bigger. Maybe I'd make it 10-bit adders or something. So it's a classic way to solve problems. Something's common in an FPGA. Okay, so this is common. I told you 10 to 30% of your design is typically arithmetic. So it's common. Should we make a special block for it? Well, let's see. I'm going to give anyone else a chance. I like you guys participating, but I want to see if anybody else has a thought. Should I make a special block or not? So if you've been waiting to answer a question, you're like, it's 50-50. Okay, and in fact, I'll even give you a lifeline. If you get flustered, you can ask the audience. Okay, I'll give you just like Who Wants to Be a Millionaire? You can call a friend, whatever you want. So, okay, so I called on Alex, and he's calling a friend. So, so Hale, sorry, Alex is using one of his lifelines. What do you think? Special block or not? Okay, what do you want to use? The ask a friend is gone. Okay, we can't do that. You got 50-50, but it's already a yes or no question. so I don't know if it's going to help you much. Or you could do ask the audience. I think that you're down to that. Put in a special block. Okay, so you think put in a special block. So you think no? Okay, so you could do this, and if we had no better ideas, you probably would do this. Okay? Isidore, you don't seem to like this. Why don't you like this? Why don't you like my special block?
I like this for the heterogeneous reason you mentioned before.
Yeah, so it's going to have a delay to get to and from it. Okay, now if we don't have any better ideas, we'd probably do this anyway. We'd just say, okay, fine, lab, adder. And you'll have parts of the design where you got one adder feeding another, and they're going to get stretched out a bit, and other parts where there's no adders, they'll get stretched out a bit, but you'd live with it. But that is one downside. So there's a cost whenever you make things heterogeneous. What else about this? How big are these full adders? So, I mean, let's say this is kind of ridiculous. Let's say it's like an 8-bit adder. Okay, so I'm going to put 4 more here. You can make ripple carries pretty fast when you just build it out of dedicated gates. So this is actually going to be pretty fast just with ripple carries, 8 full adders. Okay, so well, let me lead you to, okay, so I'm going to ask the other people then. How big are my full adders? I got 8 full adders. How much area do you think that is? A lot, little? It's tiny. It's not very big at all. Okay, so that's good. How many inputs do I have? So Isidore, how many inputs do I have? Yeah, so I've got like 16 inputs here for 8 bits, plus a CN, so sure, plus 1 CN, so maybe 17 inputs. And then out here I've got another 17 outputs, right? Actually, that's wrong, 9 outputs. I'm doing a multiplier, sorry. So it's a lot of inputs and outputs, the area in here that's doing compute is small. So that's actually good, except I have a ton of inputs and outputs, which means that this block is not going to be that small. This will approach, because routing ports are more expensive than even lookup tables when you take like 4 of them, the routing ports are going to be way more expensive than this. So I'm not going to get a good area win out of this at all because it's got so many routing ports. I might still get a delay win, but basically, yeah, many routing ports, which is bad. So this is not going to be a cheap thing. Okay, so what can I do that's better? What do you think? Okay, I'm going to give people, I'm going to give everybody a chance. Anybody else got any ideas? What can I do instead of this? Okay, Isidore, I think you have an idea. What do you think?
We're just going to stick it after the LUTs, stick it inside the ALM, have a carry chain that goes down across the, across the lab.
Yeah.
Carry chain with little colliders built into it. You're not paying any extra routing ports, and you can reuse them. Or if your add is the output of some other function, then you can actually grab it right from the LUTs. And otherwise, you're not wasting all this area on a block that may not be used.
Yeah. So I'm going to just rephrase that or summarize that. So one of our classic tricks is to harden a block, but it doesn't work well here because we need too many routing ports, okay? And we don't like the heterogeneity. We add it to the logic cluster. Why would we do that? Well, because what we're adding is relatively small, so it's not going to make our logic block much bigger, and it's going to allow us to reuse the routing ports. Whoops. Okay, so I could take this and I could say either use a LUT. Basically I can use either the LUT or I could use this adder, and I'll just hook them both to the same routing ports, and I can use one or the other. And that would be better than making an entirely separate block with its own routing ports. But I can do a little better than that still. Instead of saying I'll hook up a LUT and an adder in parallel, so I could do that. I could say basically the routing ports go here, and they go here. And then there's a mux basically allowing me to choose which of these outputs I take. So I could do that, and it allows me to reuse all my routing ports. It's better. But now I can only use the LUT or the adder, because if I use the LUT, it steals the inputs from the adder and the output. If I use the adder, same thing. So Isidore suggested something a bit more clever than that. And let me just draw that, and then we'll end for today. So okay, so what I'm going to do that's a little more clever than that. So I know I'm going a few minutes over, so if anyone has to take off, go for it. It's recorded. But this will help you sustain you through reading week, because it's a long time between programmable logic concepts, so I don't want anyone to go into withdrawal. Okay, so what is the more common thing people do is this. They basically say, let's say it's a 4-LUT, and you basically can use the 4-LUT to do part of your computation. Okay, so you take A of 0, it goes into this. B of 0 goes into this. Okay, so I've got a 4-LUT. I'm going to think of that as two 3-LUTs, because I can always think of one LUT. We can always decompose a LUT into its components. So a 4-LUT has 2 3-LUTs inside of it. And I'm going to take the outputs of those LUTs, and I'm going to add them, and I'm going to send that out. Okay, so this is part of my logic block, and I'm going to do this for many bits. I'm going to take the carry out of this, I'm going to send it to the next adder, which is hooked up to the next lookup table like this. And so on. We're not talking about that yet. Okay, so this is called the carry chain. This is just gates. It's a few gates. It's a full adder. This is hardwired. It's not programmable at all. So this is really fast. Okay, this ripple will be very quick. and eventually I'll get a carry out from the block, and I'll get all my sums. This trick, where I basically say, let's feed the output of these LUTs into the adder. So again, I've got a 4 LUT in this architecture. I've considered it, I've taken like outputs from essentially the internal 3 LUTs to get my 2 operands for the adder. If I just want to add 2 numbers, I can send A in and B in, so the lowest bit, and this 3 LUT just copies out, its truth table is just basically A. Truth table of this one is just B. Okay, it's not doing anything useful. They're just in this mode, they're feeding through their outputs. So A plus B, I basically would just make the top LUT function would be A, and the bottom LUT function would be B. And it'll do A plus B. But let's say I want to do A minus B. Okay, so A minus B can be rewritten as A, there's 2 complements, A plus B bar plus 1. Okay, so if I want to do that, well, what should I make my top LUT? If I want to do A plus A minus B. See if anyone's, what do you think? Yeah.
Well, I mean, I think, we have a 3 LUT, so we can do the plus 1 and, do the complement thing.
Well, and the plus 1, let me take the plus 1 sounds more complicated than it is. What we're going to do with that is this is a C in. Okay, so plus 1, we have a carry in. That's going to take care of the plus 1. Okay, so our steady state is all the other bits have to do A plus B bar. Okay, so what do you think the top LUT function should be? A. What do you think the bottom LUT function should be? Right, so it should be this complement of B. So we got some utility out of these LUTs now. This is why it's useful to, instead of doing what I showed there, where I kind of arranged them in parallel, I arranged them in series. So now I do have to actually have the ability to sort of skip this. So it's only partly in series. The real logic block will have a mux here. And basically, there's also a mux here that produces the 4 LUT output. So you can either use the LUT or you can use the adder after the LUT. So you can bypass the adder if you don't want it. But basically, pre-processing what goes into the adder with the LUT is useful because now I can do things like a subtractor. And I can also do some more complicated things. Like if I have a little bit more logic that's happening here, like maybe I'm selecting between 2 different inputs and then I'm adding one of them, I can fit some of that logic in these LUTs too. So this is a common way that FPGAs do it. You're reusing the routing ports and you're connecting them kind of mostly in series because of the fact that it's useful to be able to do some logic before you get to the adder. And it doesn't add a lot of delay, so it's generally a better way to do it. Yeah?
I was just like another common approaching example would be like if you're adding things and you're mapping out some values, that's like super easy to do.
Yeah, yeah, so it's easy to do a mask. We've got some AND or something. And so if it was costly, we might not do this, but it's not. So that's a very common way to do it in FPGAs. So how fast is this? So this can be made very fast, okay? This can be 10 to 50 picoseconds per bit. Which means that we're over 500 megahertz without much trouble for a 32-bit add. There's some point where this ripple structure still gets you, right? So at 10 picoseconds per bit, it's going to take quite a while, but at 50 picoseconds per bit, yeah, maybe a 64-bit adder would still be too slow. In that case, that's where on a more coarse granularity, the designer will start pipelining or using one of these parallel prefix adders. But basically, your building block is much bigger. Just small adders you just don't worry about. They just happen, they're fast, you don't pipeline and nothing. If you're doing some crypto application where you have 128-bit adds or something, you might actually have to pipeline in the adder. But it's more uncommon, and you might need one pipeline stage, not like 128. So yeah, this is what's commonly done in FPGAs. It kind of illustrates that, how do you harden something, though? And you want to think about, what am I doing to the routing ports? What are my alternatives? Should I have a special block? Should I put it inside an existing block? If I put it inside an existing block, does it go in series or in parallel? This kind of comes up over and over again. You have some function you want to make more efficient. Okay, that's it for today. Have a good reading week, and I'll post some assignments which are not due for a long time, but if you get bored, you can, well, I actually recommend you look at the RAM mapping one at least somewhat over the next 2 weeks, because I won't see you for 2 weeks.